First off, let me just mention really quickly that this is actually my first foray into the astrobiology, exoplanet habitability world, and I've really enjoyed AbSciCon conference. So thanks to AbSciCon for existing, and thanks to all the people who put this on. So I think by now we've heard enough that M dwarfs and exoplanets go together like peanut butter and jelly. They really are a really nice place to study exoplanet science, especially habitable zone exoplanets. And we've heard a lot about M dwarfs so far, but I haven't seen anyone actually put up any of their actual physical properties. And so I'm going to run through some numbers really quick because I think these are important. I think some people might not actually know this stuff. So we actually have, M dwarfs have masses from about half a solar mass all the way down to the hydrogen burning limit at 0.08 solar masses. They have temperatures from 2400 to 3800 Kelvin. There are more M dwarfs than anything else out there, star-wise. So none of us have actually gone outside and looked up and seen an M dwarf before. They're all too faint in the visible to actually see, but there are more M dwarfs than anything else. Thanks to Kepler, we know that statistically speaking, they all have exoplanets, and a lot of these exoplanets, a significant portion of them have Earth-ish-sized planets in their habitable zones. But it's really the physical characteristics that make the biggest difference in why we are so focused on them, right? So lower mass means that an Earth-sized planet in the habitable zone will induce a larger radial velocity signal, and so that's great. The larger signal is better for observers. The lower temperature means lower luminosity, and so a transiting exoplanet will have a deeper transit depth. That's also great for us. And the lower temperature also means a closer habitable zone. So all the habitable zones of M dwarfs are within the orbit of Mercury, which is about 0.4 AU. So they're very compact systems. And these shorter periods are great for detection and follow-up. So if you're waiting for something to transit more than once, you can wait days and weeks for planets in the habitable zones around M dwarfs. But a solar-type star, you've got to wait a year or so. Okay, so this has not gone, all these observational advantages have not gone unnoticed by astronomers, and I won't belabor this because we've seen all this, but we've made some really spectacular discoveries around M dwarfs recently, and equally spectacular exoplanet artwork, which is great for all of our talks. But some of this, I just want to point out that these spectral types range from M3 for GJ1132, M5.5 for Proxen, M8 for TRAPPIST-1, so we're really running the whole range of M dwarf spectral types. Okay, but the real question we want to ask ourselves, the reason we're all here, is are habitable zone planets orbiting M dwarfs truly habitable? And we've heard a lot from a lot of different speakers about how this is an extremely complex issue. We have the tidal locking scenario and all the issues that entails, the prolonged main sequence evolution, the more frequent flaring, which we just kind of talked about. We had a really nice discussion about, and increased high energy radiation, and that's what I'm really focused on today. Okay, and so one of the reasons that this increased high energy radiation is so important around M dwarfs is because the habitable zones are so close, so they're much closer. And this really great figure put together by Evgenia Shkolnik shows the absorption cross sections for a bunch of different molecules that we may be interested in, and the wavelengths for those cross sections. And so the best place to observe M dwarfs to find out what this high energy radiation would look like is in the EUV, but unfortunately we don't have something that observes there at the moment. What we do have, however, is GALEX. So GALEX is the Galaxy Evolution Explorer, what I like to think of also as a serendipitous M dwarf evolution explorer. So GALEX had two UV bands, the FUV and the near UV, which are seen here. And so the idea behind what we're doing is we want to look at a whole range of spectral types and ages of M dwarfs and constrain what's going on in this wavelength region, and to help inform the low mass models so that we can get a better idea of also what's happening over here. If that makes sense. All right, and so this is why the HAZMAT program was initiated. HAZMAT stands for Habitable Zones and M dwarf Activity Across Time. And so this is a really nice paper by Shkolnik and Barman. So this is one of the first results of the HAZMAT program. What we're showing here is the flux density ratio for FUV in blue and near UV in white for M dwarfs at different ages. And so the evolution of the UV flux in the NUV and FUV bands looks something like pretty flat for the first few 100 million years, and then a decrease as you get to, say, Hyades age, and then a further decrease as you get to field age, which we're calling around 5 gigayears. But this initial survey was done mostly with early type Ms, and as we've seen in a lot of talks, some of our most spectacular discoveries around later types, so Proxen is the M5.5, TRAPPIST M8. And so we're asking the question now, what about late Ms? Does this evolution look the same for late M dwarfs? And so the way we're going about doing this is we have a really large database of high-resolution optical spectra from quite a few different, observatories. And so we're looking at all the spectra, finding new moving group members. So moving groups are young coeval groups of stars in the solar neighborhood that provide a nice age data point for this kind of study. So we're finding new moving group members, and there are other groups that are also, we're not the only ones interested in this for many, many other reasons. So there are other groups that are looking for late type M dwarfs of moving groups, and some really nice surveys have been published recently, like the TWO Hydra Association. There was a really nice paper by Jonathan Gagne earlier this year. The Beta Pictoris moving group with an age of 24 million years. This is a paper that's submitted at the moment. It should be out soon. Stay tuned for that. The Tuck-Hoare Association with an age of around 45 million years. There's a really nice survey by Adam Krauss in 2014. We're using the Hyades sample from Goldman in 2013, so this is a really deep Hyades survey for low-mass members. And then for our older members, we're using the 8-parsec sample from David Kirkpatrick, because most things in the solar neighborhood, like really immediate solar neighborhood, are field age, so we can apply an older age to those. And so this is the sample we're working with right now compared to the sample from the Shkolnick and Barman 2014 paper. And you can see for several of these groups, especially TW Hydra, Beta Pic, and the old sample, we're not only adding more members, but we're also adding more later type members as well. These are all the ones, I should mention this, these are all the ones that actually have a Galax detection, right? So there are some that were actually observed by Galax, but were not detected, and those aren't included on these. Okay. For the next few figures, I'm actually going to break it up into two spectral type bins, early M and later M. And later M is going to stop at M6 because some of these groups, like Tuck-Hoare and the Hyades, that's basically as far out in spectral type range we want to get. So if we did M3 to M7, we'd be including some from some groups and not others. So we're stopping at M6 just for the purposes of this talk. And we could break them up into individual spectral types, but early and late kind of gets the point across. So we have early M types on the left side. So again, this is the flux density ratio versus age. And then we have late M's over here. So early M's, you can see a similar, unsurprisingly, we find a very similar trend to what Shkolnick and Barman found, which is that it's relatively flat for early ages, and then you get a drop at Hyades age, and then all the way down to the field age, it drops even further. These red points are the medians of all these distributions. So some of them have really large distributions, but there are a lot of points underneath these medians. So in general, they're representative of these groups. For late type M's, though, you'll see something a little bit different. So it looks like the near UV evolution, so the near UV flux, is pretty much consistent all the way up to Hyades age, and then drops down a little bit to field age. And this distribution, this spread, is much larger than what we have over here. But there are a lot of data points, again, under this spot. So the error bars, which we'll see on the next slide, are more representative of what this spread really is. Okay, so here are those two distributions compared to each other. Again, nothing too dramatic here, but a couple things to point out is that the relative change from Tuck-Hoare age, which is around 45 million years, to Hyades age, which is 600 million years, there's pretty much no change for the late M's, but for the early M's, we see a decrease in flux density ratio of around 2.5 times, right? And if you go from Tuck-Hoare age to field age, we only see a decrease of about 3 times what we would see at younger ages for the field age. And for the early type M's, we see a decrease by about 11 times, a factor of 11, right? And so what this is telling us is that the UV flux is remaining at a higher level for later type M's for a longer period of time, which is kind of what we expected, but it's nice to see it in the data. For late type, for the FUV, it gets a little more complicated. So what we're actually seeing Unfortunately, is the Hyades, all the Hyades members we searched, the vast majority of them were actually not detected. And so only 15 to 20% of them were detected in the early spectral type range, and only 5 to 10% were detected in late spectral types. But we can say something a little bit about this distribution. So again, pretty flat. I think I know what this is happening, but that's a different process. And they decrease quite a bit over here. So unfortunately, we don't have a lot of constraints here. Your guess as to what's going on, come on, buddy, is probably much better, much better than my guess as to what's going on. But seriously, we can say that the difference in the medians here is only a factor of 4, but for the early type stars is a factor of 35. So it's even more dramatic for the FUV what's going on with these late type stars. And really, really quickly, I just want to get into the FUV to near UV flux ratio. So we've heard about this in some of the earlier talks this week, and I actually just stole a quote right out of Harman 2015. So whether O2 and carbon monoxide can accumulate to appreciable concentrations depends on the ratio of FUV to near UV radiation coming from the planet's parent star. So this ratio is really important for figuring out the chemistry and the atmospheres that are occurring on any orbiting planets. And so what we're seeing is it's not only a function of spectral type, right? So this is the old spectral type here, but it's also a function of age. But the age is kind of interesting because the differences in ages are only showing up for the early spectral types and not the late spectral types, right? So if you want to figure out the FUV to NUV ratio, you need to know the age and spectral type kind of well. Okay, so I'll just leave up the summary and wait questions. Thank you. Thanks for the quote. Before you say anything.
Absolutely. It was my pleasure.
Mm-hmm.
Sonny Harmon, Penn State. I was curious if you have any idea. So it looked like you didn't quite get out to Lyman alpha.
Right.
And if you have some idea of how the Lyman alpha is going to dominate FUV over those age progressions.
Right. So you're absolutely right. Lyman alpha will dominate the FUV range. But I think what we're learning, and Evgenia can correct me if I'm wrong, the FUV will still scale relatively. Right, so your FUV to NUV ratio will still be similar whether or not you include Lyman alpha or not, right? Because there are other lines in there that will also be brighter or less bright.
Thanks.
No problem.
All right, we actually also have a question from Ravi Kaparapu, who is watching online. Hi, Ravi.
Hi, Ravi.
Why do late type main sequence NUV fluxes, why don't they drop as much with age?
The for late type, why do they not drop as much?
Sorry, I said main sequence. Why don't late type M's NUV fluxes, why don't they drop with age?
Yeah, so that gets into the physical reason why this is happening, which I didn't mention at all. And my guess is that it's all related to rotation, right? So late type stars don't spin down nearly as fast. What's happening is you're basically on the edge of where you become fully convective between M3 and M4, and so later M's don't spin down, so they're still rapidly rotating, and rotation related to activity, and that's why they're just staying active for much longer periods of time.
Cool, thanks. All right.
Thank you.
Thank you.